In our last episode, we saw how thrift and protocol buffers achieve efficiency by swapping bulky text names for tiny numerical field tags, a compact mapping that allows the system to identify data without the weight of full labels. Apache Avro pushes this to the absolute limit. It forces those tiny numerical tags to dissolve away, leaving a continuous stream of raw bytes. To read this, the system relies on an exact sequence, snapping data into a perfectly rigid line without a single divider. Imagine aggressively packing a moving truck with perfectly interlocking, unlabeled boxes. Without labels taking up surface area, you can cram in significantly more cargo. This digital shrink wrap creates the absolute minimum file size possible. In massive data ecosystems, shaving off even a few bytes per record saves terabytes of storage. But this density creates a massive operational hazard. If an application tries to unpack this wall of bytes without the exact original blueprint, it miscalculates lengths and types, resulting in total data corruption. Avro solves this hazard by requiring the packing application and the unpacking application to hold completely different blueprints. Think of the process like two diplomats at a negotiation table, translating a single document side by side to find common ground. On the left, we have the writer schema. This dictates the exact structure the data had when it was initially packed. On the right is the reader schema, the specific template the unpacking application is expecting to see. When the two schemas are compared, the Avro library actively translates between them. If the writer packed a field that the reader doesn't recognize, the system cleanly discards it. Conversely, if the reader expects a field that the writer didn't include, Avro injects a default placeholder to keep the structure intact. Because the translation logic handles these mismatches automatically, systems can run old and new code simultaneously. The side-by-side negotiation ensures that stripping away numerical tags doesn't break the system. This byte-level translation scales up to solve a major headache in large data pipelines, the continuous automated dumping of relational databases. If you use thrift or protocol buffers, adding a single new column to a database halts the pipeline. An engineer has to manually intervene to assign a new numerical tag to that column before data can flow again. Avro eliminates this bottleneck using dynamically generated schemas. Because there are no numerical tags to manage, the new database column links directly into the pipeline using its text-based name and resumes flow instantly. The database export process just generates a fresh schema every time it runs, and the pipeline adapts on the fly to read the new layout. By stripping away rigid metadata, engineers created a data format that is highly dense, yet capable of total automation in large-scale engineering. This leaves one logistical loophole. If the receiving application leads the writer schema to unpack the data, how does it actually find it in a sprawling cluster of servers? For massive file dumps in environments like Hadoop, Avro utilizes a self-describing suitcase method. The complete writer schema is physically embedded at the absolute top of the output file. Millions of records follow it, but that single header provides the entire structural context needed to unpack the stream. The entire Avro lifecycle starts by aggressively compressing data into tag-free byte sequences, relies on intelligent dual schema negotiation to prevent corruption, and ultimately provides a highly automated pipeline. Now that our data is efficiently packed and structured, we have to move it. In the next episode, we'll look at how these payloads physically flow between disconnected databases without getting lost.